The book shows this plot in an attempt to describe what happens when you drive oscillation. And in this case, drive effectively means push, right? Imagine that you have a mass on a spring and you kind of periodically tap it with a given frequency. If you tap it with the right frequency, where the frequency you're driving it with, so again, the period or the frequency where you're pushing it, equals the natural frequency, that's when you get a larger amplitude. And so the idea being you could drive it at actually different frequencies. If I have a pendulum, I can shake it back and forth slowly, I can shake it back and forth quickly. There's going to be a specific frequency where my amplitude gets really large, and that corresponds to the natural frequency. Now, this is all very theoretical, but the example that you might have the best sense of is a child on a swing. If you're sitting at a swing, someone can push you. And actually, they need to push you every time you get back to the beginning. That means that the frequency of your oscillations matches the frequency that they're pushing you at. If those frequencies didn't match, that would mean that sometimes they push you when you're all the way back, sometimes they run up and push you when you're in the middle. They're not pushing you at the same frequency that you're swinging. Now, you maybe know that if you're sitting on the swing, you don't even need someone to push you. You can pump your legs. And as a child, you quickly understand how to pump your legs to get the highest swing. And again, what's happening is that you're pumping your legs in the same frequency that you're actually swinging at. So again, your driving frequency is the same as the natural frequency. What is the natural frequency in this case? You can think of a swing, a person on a swing, as a simple pendulum. The mass is largely concentrated to be at the end, and so you would use the length of the chains in this case, and then the gravitational coefficient. As we've looked at, the period of a simple pendulum doesn't depend on the mass. So theoretically, if a small child sits on the swing versus an adult, the frequency would be the same. So that's the idea of driven oscillation. Now, the thing that then happens is resonance. So resonance is the idea that the frequency you're driving it at matches the natural frequency. So in this case, we're looking at different external frequencies. So again, how are you driving it? And then the natural frequency is 2 Hertz, so twice a second. Now, if you have a heavily damped system, remember that B is our damping coefficient. So if we have a heavily damped system, i.e. there's a lot of drag, so a lot of friction or a lot of air resistance, such as a child on a swing, you don't see that much. However, as the air resistance or friction, whatever damping force you're thinking about, decreases, this amplitude increases. And in this case, there still is some damping. And in fact, mathematically, if there was no damping, you could get infinite amplitude if you drove your system at its resonance frequency. Now, this is an interesting case because in the real world, is there ever really zero damping? No. This is where, again, you should think about modeling, that we model air resistance as being 0, or we model friction as being 0, but those really are approximations. Unless we're talking about something in space, really there's always some air resistance. So, one example, though, of when you have a system with very little damping, so a system that resonates really well, and you drive it at its natural frequency, well, the best example of that is shattering a glass. And the book talks about this, but this is really a beautiful example of this. That if you take a really cheap wine glass and you tap it just with your finger or a pencil, you hear a little bit of a sound, but it kind of is more of a thud. And that is actually that the system has a lot of damping. If you have a really nice wine glass and you tap it, it rings like a bell. And that actually shows you that the system has very, very little damping. Now in this case, this actually has to do with the mechanical properties of the glass, not just air resistance, but it would take a really long time for those vibrations to die out if you had very little damping. And that, again, what happens if you tap it and it rings like a bell. So if you take a really nice, expensive wine glass and you tap it, you hear that sound. If you then sang that sound really loudly and you were right on the right frequency, or you had an instrument that was playing the right sound, and again, the right frequency, you would cause so much vibration to happen that it would shatter. And this isn't just a magic trick. This is something you can really do, but you have to have a nice enough wine glass so that damping is small enough, and you have to be right on the frequency. So that's why this is usually done with opera singers, that they have good enough control of their voice that they can really hit the right tone, and most of us can't actually do that. So we're not really going to go through the math on this because the math gets really complicated. I'm sure this is something that you get to study if you take Math 309, differential equations, but we're not going to worry about the math in this class. But to just bring home the terminology, since mostly this section introduces new terminology, natural frequency is the frequency that the system wants to actually oscillate at. And what that means is this is the frequency that we have been calculating for simple harmonic motion, right? We've said what is the frequency of a mass on a spring, or what is the frequency of a pendulum. And in this case, when we talk about frequency, we mean F, and remember that up till now we've usually been talking about omega, and the difference is simply a factor of 2 pi. But so whenever we calculate the frequency of our system, that is the natural frequency. So the resonance frequency is the same thing as the natural frequency. What is the frequency that it wants to vibrate at? Same thing. The difference being that resonance frequency is when we're usually talking about driving it. So driving frequency is coming from the outside. So again, if I'm singing a tone, that note has a frequency to it. I'm then trying to excite the glass with that external driving frequency. Or in the case of pushing someone on a swing, we could measure the amount of time in between my pushes, that would be the period, and we could calculate frequency from that. Resonance is then when you are pushing your system or driving your system at the frequency that it naturally oscillates at. So that's what's going on here. Again, mathematically, we're not going into it, but it's an interesting thing to think about since it's something we see around us in the real world a lot, and we'll actually come back to it in the second semester of physics when we talk about waves a little more and talk about musical instruments. But musical instruments are all about natural frequencies and resonance.